Blackbody radiation. Here we go. Before we go detail on the blackbody radiation, the explanation of the blackbody radiation, let us differentiate between any object and blackbody. Any object, when there is radiation come into it, it will absorb part of the radiation. The another part will be reflected back. After some time, they absorb the radiation, it will emit again all the absorbed radiation. So this is any object. But for blackbody, it is a little bit different. Blackbody will absorb all the radiation incident onto it. That means there will be no reflection. But also the same, after some time, the absorbed radiation, all the absorbed radiation will be emitted. And for this case, the radiation emitted is called blackbody radiation. So now we can define what is blackbody. Blackbody is the object that absorbs all radiation incident onto it. Okay, just now I said that any object will radiate the radiation, will emit radiation, alright? But you may ask me a question like this. Why can't we see any object emit radiation? Which means, why can't we see anything glowing with some radiation? The answer is because energy of the radiation absorbed or emitted depend on the temperature of the object. Which means, the radiation that we can see depend on the temperature of the object. Where the higher the temperature of the object, the higher the energy of the light that we can see. Okay, if we look at this graph is actually the plot of intensity versus energy. For low temperature, we can see that the peak of the graph lies on the low energy. If we increase the temperature, the peak of the graph lies at the higher energy. Okay, if we increase the temperature further, the peak of the graph lies on the higher energy than before. Okay, so we can see here that the peak of the graph is actually what energy of light that we can see. Now I want to show you some data. For temperature is, if the temperature of the object is 2000 Kelvin, the emitted light will be infrared. So that's for the object that is 2000 Kelvin, we cannot see any color of light because the radiation come out is infrared. This is the reason why we cannot see any object glowing, because we at the room temperature, even very low than 2000 Kelvin. For 3000 Kelvin, the light emitted is still infrared, so we cannot see. Okay, for 4000 Kelvin, it become red. For 5000 Kelvin, it become yellow. So let's say we have a metal ball. How we want to make it glow with red? So we must heat the metal ball until the temperature become 4000 Kelvin. And then we can see the metal ball glowing with the red color. If you want the metal ball to glowing with the yellow color, we must heat the metal ball up until 5000 Kelvin. Now we see how classical mechanics fail to explain the blackbody radiation. This is the attempt done by Wien and Rayleigh, which is they use the classical approach to explain the blackbody radiation. Wien do a theory and get this equation, and this equation they can plot a graph which is get this kind of a graph. Rayleigh do the theory but different approach. He get this equation and this graph. Okay, if we combine these two graphs, the graph will look like this. Okay, I will explain what is ultraviolet catastrophe after this. Okay, however, the actual graph for blackbody radiation look like this. This have like a bell shape. But if we combine the two, Wien and Rayleigh, we not get the bell shape, which is we have some value of frequency where the intensity of light is infinity. Alright? Okay, so what we can conclude about this, Wien only explain well for high frequency. If you can see here, Wien graph is slightly to the actual graph, but at high frequency only. Rayleigh only explain well for low frequency. For the Rayleigh graph, we can say it fit well for the low frequency only. But in the region at the middle, they cannot explain. There exists some value of frequency with infinity intensity, which is we call ultraviolet catastrophe. The classical mechanics have that, which is some value of frequency where the intensity is infinity. Okay, and this is what we call ultraviolet catastrophe. So this is the failure of the classical mechanics. Now, Planck come up with some new idea to explain the blackbody radiation. So he success. So this is the detail how the blackbody can absorb the light and then emit the light again. Okay, this is a blackbody. Planck said the blackbody, inside the blackbody, there is consists submicroscopic charge that we call a resonator. Okay, when radiation incident on the blackbody, the radiation energy will be absorbed by the resonator. And what happened? The resonator will gain the energy and vibrate. Okay, it will vibrate after absorb the radiation because it gain energy. The key thing is this. Einstein said Planck said resonator can only take some value of energy, this is the idea where the energy is quantized. So he says that this resonator will only take the value of energy E equal to NHF. So the energy that this resonator can take is HF, 2HF, 3HF, and so on, not another value of energy. Okay, so this is the quantization of energy. So after some time, the resonators stop vibrate, which is they lost their energy. So the lost energy will become the blackbody radiation. So that's how blackbody can absorb the energy, the radiation, and then emit back. So by using all of the idea, which is the quantization of energy, Planck are able to come up with some new equation. Okay, and this equation really fit the experimental data of the blackbody radiation, which is he get this graph. Thank you for watching. Bye bye.